Alright, we are on to lesson 5 of the last vectors unit. This lesson is on the intersection of lines in both 2-space and 3-space. So now that we know how to write both vector and parametric equations of lines, we can solve systems of lines in 2-space differently than you would have back in grade 10. But we can now also solve systems of lines in 3-space. And in this lesson, I'm going to review with you all the different possibilities that could happen when we're trying to find the intersection of two lines. We know that lines can be parallel, and if they're parallel, they're either distinct, meaning no point of intersection, or they're coincident, meaning an infinite number of points of intersection. Or the lines could be not parallel to each other, which in 2-space means they intersect, but in 3-space, they could intersect, or they could be skewed. So I'm going to take you through how we can tell from the equations of the lines and our solving process which of these 4 scenarios we have, and if we can find a point of intersection, I'll teach you how to find that. So when you're ready to learn all of this, head on over to jensenmath.ca so you can get a blank copy of the lesson. We are in the Calculus and Vectors course, and we are in the 3rd unit, lesson 5, intersections of lines. You can get a blank copy of the lesson here. You can get the practice problems by clicking on worksheet, and after you've tried the practice problems, you can check your solutions by clicking on worksheet solutions. So when you're ready, let's get started. So part 1 of this lesson, we're going to be looking at the intersection of lines in 2-space. So before I go over this table with you, I just want to show you what the questions would look like. I'm going to give you a system of equations of lines, and they could be in standard form like those two, or I could give you 2 lines where I give you the vector equation of the lines. And you're going to learn how to figure out, first of all, if there is a point of intersection of the pairs of lines, and if there is, what is the point of intersection? So let's review the 3 scenarios that could happen while we're trying to find the intersection of 2 lines in 2-space. If the 2 lines are not parallel, meaning they have different slopes, then I know they would intersect at a single point. If the lines are parallel, they could be parallel and distinct like those two, meaning they never cross. There is no point of intersection. Looking at the equation in slope y-intercept form, I see they both have the same slope, but different y-intercepts, so I know they're parallel and distinct. Or they have the same slope and the same y-intercept, which means they're in fact the same line, meaning there are an infinite number of solutions. There are infinite points of intersection. So let's do a few examples, one for each of these scenarios, so that you see algebraically what happens when we try and solve a system of equations based on what scenario we have. Alright, for example 1, we're doing 3 systems of lines. B and C, you're given the vector equations of lines. That's what we're going to focus on. But part A, I'm just giving you a warm-up. You're given the standard form equation of the line. So we can solve this just like you did back in grade 10. We can solve it using elimination or substitution. And since the like terms are already lined up, I think I'll use elimination. So I need to eliminate either the x's or the y's. So let's multiply line 1 by 3 and line 2 by 2 so that the x's both have a coefficient of 12, and then I can eliminate the x's. So 3 times line 1, I'll call that equation 1, would give me 12x minus 18y equals negative 30. And multiply line 2 by 2, and I would get 12x minus 18y equals negative 30. Hey, notice they're exactly the same line. They're the exact same equations. So these lines are parallel and coincident. There are an infinite number of points of intersection because the lines lie on top of each other. Let me just finish this process to see what you would get algebraically. When I try to eliminate these x's, since their coefficients have the same sign, I would subtract. I would do 12x minus 12x, which gives me 0x. And then I would also subtract all other pairs of like terms, negative 18y minus negative 18y. That's 0, so I don't have to write anything. Equals, on this side, negative 30 minus negative 30, that's also 0. So you get 0 equals 0. When that happens, that tells us that the 2 lines are always equal to each other. Let me show you what this looks like on a graph. So there's the first line, 4x minus 6y equals negative 10, and if I graph the second line, 6x minus 9y equals negative 15, it just goes right over top. They're the exact same line. So in 2-space, if you're solving a system and you get 0 equals 0, you know that they are parallel and coincident. Therefore, parallel and coincident. That means they are the same line, and there are an infinite number of points of intersection. Let's try part B. Part B, we're given the vector equation of the 2 lines. Whenever you're given the vector equation of the two lines, it's always going to be useful to rewrite the equations in parametric form. So let's write the parametric equations of the lines. So for line 1, the parametric equations would be x equals 1 minus 6s, and y equals 5 plus 8s. Line 2's parametric equations, x would equal 2 plus 9t, and y would equal 1 minus 12t. Okay, once you have the parametric equations, now what you do is you equate the x variables from the two lines, and you also equate the y variables of the two lines. Then we get two equations that both have two variables, s and t, that we can solve for using elimination. So equation 1, let me equate the x variables. 1 minus 6s equals 2 plus 9t. And let me rearrange this so that it's in the format that'll make elimination easiest. And now let me find equation 2 by equating the y variables. So 5 plus 8s equals 1 minus 12t. And now once again, let me rearrange this so it's in the same format I rearranged this one into. Alright, now that I have the two equations, I can solve for what values of t and s make the two equations true. So let me eliminate the s variable by making both of the coefficients be 24. So I'll multiply equation 1 by 4, and I'll multiply equation 2 by 3. And now since the coefficients of the s's are opposite signs, I could add them to eliminate them. So I'll add all pairs of like terms. So negative 4 plus 12, that's 8, equals 36t plus negative 36t, that's 0. And 24s plus negative 24s is also 0. So I get 8 equals 0. What does that tell me? It tells me that the lines never intersect. There are no way those two equations could be equal to each other. There are no set of values of t and s that make those two equations equal. So I can say, therefore, no solutions. The lines are parallel and distinct. Now let me just prove that to you with a graph. So here are those two lines, and you can see that those two lines never intersect. They're parallel and distinct from each other. Now we could have done this question a different way, maybe a little bit of a shorter way. We could have figured out their parallel just by comparing their direction vectors and seeing if they were scalar multiples of each other. And after we noticed that the direction vectors were scalar multiples, we could have just checked to see if a point from one of the lines was on the other line. If it was, then they would be parallel and coincident. But if it wasn't, we would verify they were parallel and distinct and had no solutions. Let me just show you what I mean. So up here are my two direction vectors. Direction vector 1 is negative 6, 8, and direction vector 2 is 9, negative 12. If these direction vectors are scalar multiples of each other, that would tell us that the two lines are parallel to each other. So we could check, is there some scalar k that I can multiply this direction vector by to get this direction vector? If there is, then the direction vectors are collinear and the lines are parallel. And notice, if we multiply this direction vector by negative 1.5, it would equal this direction vector. So therefore the lines are parallel. And then all we would have to do is we would have to check and see, is this point from line 1, is it on line 2? So just plug that point into the parametric equations of line 2, 1, 5, solve both of those equations, and see if there's a value of t that makes it true. If we solved this one, we would get t equals negative 1 over 9. If we solved this one, we would get t equals negative a third. So different t values. That would tell us that this point from line 1 is not on line 2, but they're parallel. So we just figured out this point here is not on line 2, but they're parallel, so we just proved they're parallel and distinct, therefore no solutions. So that's just another way we could have come up with the answer that there were no solutions and that the lines are parallel and distinct. But the algebraic process will tell you that as well if you go through all of those steps. Okay, part C. Once again, we're given the vector equation of two lines. Let's see if these two lines intersect. Well, actually, I can tell right away that these lines are going to intersect because if I look at their direction vectors, I notice they are clearly not scalar multiples of each other. So these lines are not parallel. So they are going to intersect at a point. Let's see how we find that point. So let's start by writing the parametric equation of the lines. And once you have the parametric equations, we can equate the x variables and equate the y variables and get two equations. So I will equate the x variables. And now I will equate the y variables. And once you have two equations that each have two variables, we could solve for those variables using substitution or elimination. I'm going to do elimination, so let me rearrange these so the variables are on one side and the constant is on the other. Alright, so now I need to either eliminate the t variable or the s variable by adding and subtracting these equations. So I'm going to eliminate the s variable, so I'm going to make the coefficient of this s be -6 and the coefficient of this s be 6, and then what I could do is add the equations and the s's will eliminate. So to make this be a coefficient of -6, I would have to multiply this whole equation by 2. So 2 times equation number 1 would give me 10 equals 6t minus 6s, and I would have to multiply equation 2 by 3 to make this be a coefficient of 6. So 3 times equation 2. That would give me 18 equals 15t plus 6s. Now to eliminate these s's, I'm going to add the equations since they have opposite signs. -6s plus 6s is 0s. That will eliminate the s's. And let me add the other pairs of like terms as well. 10 plus 18 is 28. And 6t plus 15t is 21t. And -6s plus 6s is 0. Now solve for t. T equals 28 over 21. 7 goes into both of those numbers. It goes into 28 4 times and into 21 3 times. Now, normally you would then think, okay, well now I need to solve for s. But when working with lines in 2-space, I actually don't. The fact that I was able to solve for a value of t tells me that these two lines do intersect. And they intersect when the value of t is 4/3. And I could figure out exactly where line 2 is based solely on the variable t. So I don't have to bother solving for s, because if I solve for s, it would be a little redundant. I mean, I could solve for s, yes, but then when I plug it into line 1, I should get the exact same answer for x and y as I got for line 2 when I plugged t into line 2. So, I mean, it's a way you could verify your answer. If you were doing an evaluation, I would, yes, solve for s and then verify you got the same answer as when you plugged 4/3 in for t into line 2. But it's not necessary here. Now, I should mention, when we work with lines in 3-space, it will be a necessary step to solve for the other variable, because we're going to have to do a check to see if the lines are skew or not. In 2-space, we don't have to worry about that. Skewed lines is not an option. So we could stop right here, t is 4/3, and then solve for the point of intersection by plugging that into the equation of the line that has t as the variable. So line 2. Okay, so I just copy and pasted the parametric equations of line 2 here just as a reference. And now if I want the x coordinate of the point of intersection, I just have to plug 4/3 into the x equation. And if I do this, I get x equals -2 plus those 3's cancel, so -2 plus 4, x equals 2. Now let's get the y coordinate by plugging 4/3 into the y equation. Y equals -2 plus 20/3. And I'm going to need a common denominator here, so let's rewrite -2 as -6/3. And this will give me 14/3. So my point of intersection, therefore, the point of intersection is 2, 14/3. Okay, that's it for solving systems of lines in 2-space. Let's move on to solving systems of lines in 3-space. Alright, part 2, intersection of lines in 3-space. There are now 4 options for what could happen. Now, if the lines are parallel, the same 2 options, they could be parallel and distinct, or I think it's the bottom option here, they could be parallel and coincident. Now when I say parallel, we could easily tell that by looking at the direction vectors and seeing that they're scalar multiples of each other. So in both those scenarios, the direction vectors are scalar multiples of each other. In fact, they were equivalent to each other. But if they're parallel and distinct, notice they never intersect. Those 2 lines never intersect. But if they're parallel and coincident, the lines lie right on top of each other, so there are an infinite number of points of intersection. And we'll talk about how we could tell which of those two scenarios we have. What we're going to focus on, though, are now there are two scenarios for what could happen if the lines are not parallel to each other. If they're not parallel, we could get a point of intersection, but we could also not get a point of intersection. The lines could be skewed. So if we look at the two equations in both of those scenarios, notice the direction vectors are not scalar multiples of each other in either of those scenarios. But in one of the scenarios, we get a point of intersection. In the other one, we don't. So I'll take you through algebraically what's going to happen for us to be able to tell which of those scenarios we have. And let me just give you a visual demonstration of what those skewed lines look like so you can get a better understanding of what I'm talking about. Alright, these lines, they look like maybe they intersect at this point right here, but as I rotate, notice they actually never cross. Those two lines we would say are skewed lines. They're not parallel, but they never cross, so they're skewed. Alright, let's solve for three intersections of lines in 3-space. We'll do example 2, A, B, and C. For each of those examples, we're going to go through the same process. The first step, let's check if the lines are parallel. Let's check if the direction vectors are scalar multiples of each other. If they are, then they're parallel. And if they're parallel, they're either parallel and coincident or parallel and distinct. How can we tell between the two? We could just test a point that we know is on one of the lines and check and see if it's on the other line. If it is, then it's on both lines, and the lines are parallel and coincident, meaning there are infinite solutions. If it's not, then that means the lines are parallel and distinct, and there are no solutions. If when we check if the direction vectors are scalar multiples, we find that they are not scalar multiples of each other, that tells us that the lines are not parallel, and they either are skewed, or they have a point of intersection. The only way we can tell that is if we actually go ahead and try to solve algebraically. And once we solve for the parameters that make two of the coordinates be the same, we have to check if those parameters also make the third coordinate be the same. If they do, then we have a point of intersection. If they don't, then we have skewed lines. That'll make more sense, I think, as we actually go through a question. Part A. Step 1, always check to see if the lines are parallel. So let's check if these direction vectors are scalar multiples of each other. We're just going to check, is the direction vector 1, 5, -2 a scalar multiple of the vector 2, 10, -4? So could I multiply direction vector 1 by some scalar value and make it equal to direction vector 2? The answer is yes. If k was 2, they would be equivalent to each other. K equals 2 satisfies that equation. Therefore, line 1 and line 2 are parallel. So they're either parallel and distinct, like that, or they're parallel and coincident, meaning the lines are right on top of each other. So how do we tell which of the two scenarios we have? Well, I know this point 5, 11, 12 is on line 1 because the position vector points to a point on the line. But is that point also on line 2? If it is, then the lines are on top of each other and they're parallel and coincident. If it's not, then they're parallel and distinct, meaning there'd be no solutions. So let's check. Is point 5, 11, 2 on line 2? So let me write the parametric equations of line 2. And now let me check if the point 5, 11, 2, the point from line 1, check if that point is also on line 2. So I will set x equal to 5, I'll set y equal to 11, and I'll set z equal to 2. And now I'll solve these three equations. If I get the same answer for t in all three equations, then I know the point 5, 11, 2 is on line 2. If I get different answers for t, then I know it's not on the line. So let me solve these equations. If I solve the first one, I get t equals 2. If I solve the second one, I get t equals 2. But if I solve this one, I get t equals 7 over 4. So since there is not a single value of t that makes all three of those equations true, I know the point 5, 11, 2, the point from line 1, is not on line 2. Therefore, the lines are parallel and distinct. Therefore, no solutions. They never intersect. Now, I should mention we could have also just tried to solve this algebraically. We could have written the parametric equations of line 1 and then equated the x's, the y's, and the z's, got 3 equations, tried to solve for s and t. But if we did that, at a certain point in that whole process, when we were trying to figure out when one pair of either the x, y, or z variables were equal to each other, right, for what values of s and t, we would have got to a point where we weren't able to find a solution. We would have got like 10 equals 0 or something like that. And that would have told us, therefore, there were no solutions. But I think it's much faster if we do that check at the beginning just to see if the lines are parallel. So that narrows down the options for what could happen right away. And let me just show you what these lines look like in GeoGebra, just so we can verify what we found. Here are those two lines. Notice those lines, yes, are parallel, but the point from line 1, point P, point 5, 11, 12, is definitely not on line 2. So these two lines are parallel and distinct. They never cross. There is no point that those two lines share. Part B. So once again, two lines in 3-space. We have the vector equation of these lines. I should start by checking if the lines are parallel. Is direction vector 1 a scalar multiple of direction vector 2? Is the direction vector 2, 1, negative 3 equal to a scalar multiple of the direction vector 1, 5, 5? No, there's nothing I can multiply this vector by to make it equal to this vector. Right, what would I multiply 1 by to make it 2? 2. But if I multiply this by 2, it doesn't give me 1. But anyways, if you weren't sure, you could set yourself up 3 equations, one for the x components, 2 equals 1k, one for the y components, 1 equals 5k, and one for the z components, negative 3 equals 5k, and then solve all 3 of these, and you would get different answers for k. This would tell you that the direction vectors are not scalar multiples of each other, and therefore the lines are not parallel. But that's a bit of an unnecessary step. All that you would need to show for this is just show that they're not scalar multiples of each other. Therefore, not parallel. So since they're not parallel, we've narrowed it down to 2 options. They either intersect at a point, or they're skewed lines. So let me show you how we tell what we have. We actually just start trying to solve the system and see what happens. So let's write the parametric equations of both lines. Okay, once you have the parametric equations of both lines, now we generate 3 equations by equating each of the variables. So equate the x variables together, and we get 7 plus 2s would equal 3 plus t. And I'm going to rearrange this so the constant is on the left and the variables are on the right, and I'll call that equation 1. Now I'll equate the y variables, 2 plus s equals 9 plus 5t, and I'll rearrange this one as well. Negative 7 equals 5t minus s. That's equation 2. And same thing for the z variable. Negative 6 minus 3s equals 13 plus 5t. Rearrange this one. Negative 19 equals 5t plus 3s. Okay, I have 3 equations. All 3 of those equations have the same 2 variables. Now, there are 2 things that could happen. There is either a single set of t and s values that make all 3 of those equations true. And that would tell us that the lines intersect at a single point, and we could find that point by plugging in either t or s into line 1 or line 2. Or, instead of finding a single set of t and s values that work for all 3 equations, we might end up only finding a set of t and s values that work for 2 of the equations, but not for the 3rd. So let's see what we have to do to finish solving this question. We have to pick a pair of these 3 equations. Doesn't matter which pair. I'm going to pick equation 1 and equation 2, and then we'll solve for both t and s using substitution or elimination. I will use elimination. So let me eliminate the s's. So I can leave equation 1 exactly as it is, but I would have to multiply equation 2 by 2. And I can eliminate the s's if I subtract these 2 equations. So let me subtract all the like terms. 4 minus negative 14 is 18. T minus 10t is negative 9t. Negative 2s minus negative 2s is 0s. So I get this, which I could then solve and get t equals negative 2. Now when we were in 2-space, we stopped there and just plugged that in and said that was our point of intersection. But we can't do that when we're in 3-space. We don't know if these lines intersect or not. They could be skewed lines, so we have to keep going. We have to solve for the value of s that makes these two equations true by subbing t equals -2 into either equation 1 or 2. It's important we're doing it into 1 or 2 and not 3 because those are the two equations we use to get t equals -2. So I'll sub it into equation 1. 4 equals -2 minus 2s. Now solve for s, and I would get 6 equals -2s, s equals -3. So these two values, this pair of values for t and s, they make equation 1 and 2 true. So those came from the x and y variables of line 1 and line 2. So for those values of t and s, I know that the x and y coordinates are going to be the same. But will the z coordinates be the same? I actually have to check and see if these two values for t and s also satisfy equation 3, which came from the z coordinates of the two lines. So this is a necessary step. We have to do this. So I'll separate into left side, right side, and check if it makes left side equal to right side. So now let me sub them in into the right side of the equation. I get -10 minus 9, that is -19, so left side equals right side. Therefore, the value for t and s that make the x and y coordinates the same also make the z coordinates the same, so therefore the lines do intersect at a point. I can find that point of intersection by either subbing t equals -2 into line 2, because that's the line that has the t variable for its scalar, or by subbing s equals -3 into equation 1, because that's the line that has s as its variable. It shouldn't matter which one I do, I should get the same point for both because that's where they intersect, so it shouldn't matter. Let's sub t equals -2 into line 2. So I just copy and pasted the parametric equations for line 2 here, just so I could remember them. And now let's sub t equals -2 into each of those three equations and get the x, y, and z coordinate of the point of intersection. So x would equal 3 plus -2, so x would equal 1. Y would equal 9 plus 5 times -2, so y would equal -1. And z would equal 13 plus 5 times -2, so z would equal 3. So the point of intersection is the point 1, -1, 3. Let's verify that in GeoGebra. Okay, here are the two lines. Let me input the point that we found as the point of intersection, 1, -1, 3. And yes, we can see that in fact that is where the lines intersect. Last example, you can probably guess what this one is going to be, but let's go through it anyway. Notice the direction vectors, once again, are not scalar multiples of each other. So I could just write a little comment here saying direction vector 1, 2, 3 is not a scalar multiple of direction vector 2, -1, -1. There's no scalar value I could plug here to make this vector equal to that vector. So therefore, they're not parallel. So they either intersect at a point or the lines are skewed. So let's go through our process to see what happens. Well, the last example we did, they weren't parallel, but they did intersect at a point. This time they're not. They're going to be skewed, but let's see what happens when we do our solution process. So we always start by writing the vector equations in parametric form. And once they're in parametric form, we can make our three equations by equating the variables. So equation 1 I'll create by setting the x coordinates equal. And then I'll rearrange it once again to get the constant by itself on the left. Equation 2 will be from the y coordinates. And equation 3 from the z coordinates. And once you have all three equations, we pick any pair of two of those and solve for t and s. So I think I'm going to use equation 2 and 3 because if I subtracted those equations right away, the t's would eliminate. So let me just rewrite equation 2 and 3 here. If I subtracted these two equations, the t's would eliminate. So let's subtract all pairs of like terms. -4 minus -3, that's -1. Negative t minus negative t is 0. And negative 2s minus negative 3s is 1s. So I get s equals -1. And now I sub that value into equation 2 or 3 to get the value of t that makes those two equations true. So I'll just sub it into equation 2. -4 equals negative t minus 2 times s, which is -1. So -4 equals negative t plus 2. T would equal 6. So we have figured out that for this pair of s and t values, equation 2 and 3 are both true, meaning that the y and z coordinates of the two lines will be equivalent for those s and t values. But will their x coordinates also be equivalent? So we have to check and see, do those s and t values satisfy equation 1? So write equation 1 separated into left side, right side, and we'll test those s and t values. Equation 1 was 3 equals 2t minus s. So on the right side, let's sub in our t value and our s value. And we see 3 does not equal 19. Left side does not equal right side. So that means for those t and s values, the y and z coordinates are equal, but not the x coordinates. So therefore the lines do not intersect. These lines are skewed. Therefore, no solution. The lines are skewed. And let me just show you these two lines in GeoGebra. So here are those two lines. Notice they are not parallel, but they do not intersect. So they are skewed lines. Alright, so that's it. We've gone through all the scenarios. Make sure you try the practice questions. And that's it.